A polar molecule has polarity, otherwise known as a separation of charge. Molecular polarity is measured by dipole moment. So molecules that are polar have a dipole moment, while molecules that are nonpolar do not have a dipole moment. Okay, so separation of charge in a molecule means they're polar and they have a dipole moment. Molecules that are nonpolar have no separation of charge and do not have a dipole moment. So you are going to have to be able to determine if a molecule is polar or nonpolar. So let's look at the criteria for nonpolar molecules first. There are far fewer nonpolar molecules. So if you can identify something as nonpolar first, then it's just easier to go through this criteria first, because if it's not nonpolar, then you know it's polar. So the criteria for nonpolar molecule is high symmetry. It must be AX2 linear, where X is the same atom, so for example, or same element. So for example, carbon dioxide, where C would be our central atom A, and O would be our outer atom X. AX3 trigonal planar, an example is boron trihydride, where boron is our central atom and hydrogens are the outer atoms. And AX4 tetrahedral, where carbon would be our central atom and hydrogen is our outer atoms. So important to consider is that X has to be the same element and there cannot be any lone pairs on the central atom. If you remember, if we have AX2 and it's linear, there are no lone pairs in the central atom. AX3 trigonal planar, no lone pairs in the central atom. AX4 tetrahedral, no lone pairs in the central atom. So polar bonds and polar molecules. Requirements for a polar molecule. There have to be polar bonds, which means there's a difference in electronegativity, and there has to be a non-uniform distribution of polar bonds. And this happens when the molecule is not very symmetric. It can have some symmetry, but for it to be nonpolar, it has to be highly symmetric. So high symmetry. So I find it easier to first determine whether a molecule is nonpolar or not, because if it's not nonpolar, then it has to be polar. Now, one of the things that I want to make clear is there's a difference between bond polarity, or a bond dipole, and a molecule polarity, or molecule dipole. So let's take a look at carbon dioxide. Oxygen has a higher electronegativity than carbon, and carbon and oxygen form a very polar bond. Oxygen is more electronegative, so there's a partial negative charge on each oxygen. Oxygen pulls those bonding electrons toward itself and forms a partial negative charge. You may see throughout your chemical career these color-coded shadings of electron density. Electron density is highest where it is red and lowest where it is green. So this graphic here shows a high level of electron density on the oxygens and low level on the carbon, showing that the bonds are in fact polar. However, the molecule is not polar. These dipole moments in essence cancel each other out because of the high polarity. So you can have polar bonds, but if those polar bonds are in a highly symmetric molecule, then the molecule will be nonpolar. Okay. So here's an example of a molecule that has polar bonds and the molecule is polar. If we look at water and we look at its Lewis dot structure, I see that there are lone pairs on the central atom. As soon as you see lone pairs on that central atom, you know that it has to be polar because it's not nonpolar. And if we look at the directionality of the dipole moment in the bond, oxygen is more electronegative, So it's going to pull those bonding electrons toward itself and gain a partial negative charge. So if we look at the dipole moment of the whole molecule, the oxygen will have the negative charge. It kind of is the average between these two dipoles. And I'm not sure what this is here. I'm just going to eliminate that. Now, dipole moments can actually be measured, and the units we use for dipole moments are dBi, capital letter D, and this shows the apparatus that is used, or a graphic of part of the apparatus that's used to measure a dipole moment. Molecules in the gaseous phase are placed in an electric field, and if the molecule is polar, then the positive end of that polar molecule will become attracted to the negative plate here, while the negative end of the molecule will be attracted to this positive plate. And here are some examples of measured dipole moments for several different molecules, and then also listed are the directionality of the bond dipole moment. So if we look at HF, there's only two atoms here. This is a polar bond. Fluorine has a higher electronegativity than hydrogen, and this dipole moment is 1.91 dBi. Water is a polar molecule. It has a dipole moment of 1.85 dBi. Ammonia, a dipole moment of 1.47. This molecule here is known as trichloromethane. It has a dipole moment, and this molecule, its name is trichlorofluoromethane, also has a dipole moment. So we're going to look at how you can determine on your own, without knowing what the measured dipole moment is, whether a molecule is polar or not. So let's first look at diatomic molecules, which are molecules that are made up of two atoms. If the atoms are the same, the molecule is nonpolar, or if the atoms have very similar electronegativities. If the atoms are different and the difference in electronegativity is greater than 0.4, then the molecule is polar. So for example, HF is diatomic molecule. These two atoms, hydrogen and fluorine, have a difference in electronegativity that's greater than 0.4, and it's polar. Now, if the molecules are not diatomic, the criteria is a little more involved. The first thing you want to look at is the identity of the atoms that are bonded to the central atom. If they are different, then the molecule is polar. You don't have to go any further. So for this example, carbon is our central atom. It has two different atoms bonded to it. It's polar. If we look at trichloromethane, the central atom carbon has two different elements bonded to it. It's polar. If we look at trichlorofluoromethane, there are two different elements bonded to carbon. It is polar. So when that is the case, when there's two different elements bonded to the central atom, you know that it's polar. Now, sometimes you'll have a polar molecule where all of the same atoms are bonded to the central atom. So if we look at boron trifluoride and ammonia, one of these is actually polar, and you probably know if you've been paying attention. But the point is, you can't just look at the formula. So if we have a central atom that has the same atom bonded to it, what we have to do is we have to draw out the Lewis dot structure. And if there are lone pair electrons on the central atom, then the molecule is polar. So if we look at ammonia, we draw out its Lewis dot structure, there is a lone pair on the central atom. So that means it is polar. If we look at oxygen, it has two of the same atoms bonded to it. How do we know? How do we know that oxygen is not AX2? That has two of the same atom bonded to the central atom. Well, we have to draw out its Lewis dot structure. And when we do, we see there are lone pairs on the central atom. So hopefully this criteria will help you identify which molecules are polar and which are not. Good luck.